Okay, so we're going to start by finding the area of this triangle. This is an equilateral triangle, and this process is pretty much the same for isosceles triangles. So the area formula for a triangle looks like this, right? Or you could say base times height divided by 2. So I have to use 18 as the base because all the sides are 18. But I have to figure out what the height is. The height can't be 18 because I need the height to be perpendicular to the base, right? So if the bottom of this triangle is my base, then the height is going to look like this. This is going to be my height. I got to figure out what that is, okay? So the bottom's 18, so these two sides are 18. Let's put that in, okay? And these two triangles that I drew, the two half triangles, are going to be congruent because I could do reflexive and then HL, so they're congruent. And what you need to remember is that this height is going to divide the 18 in half. So I'm going to get 9 and 9, okay? And what that's going to do is that's going to allow me to find H because I've got a right triangle here and I can use the Pythagorean theorem on that, okay? So let's see. I'm going to do a little side problem here. A squared plus B squared equals C squared. So the hypotenuse here would be the 18, so that's got to be the C, right? So H and 9 are the A and B. Those could be in either order, but you need to have the 18 isolated over here, okay? Let's see, 18 squared is 324. And I'll subtract 81. Early in the morning, so I'm going to double check with my calculator, make sure I don't mess up. So I got 243, h squared equals 243. Then I take the square root of both sides, and it's going to be the square root of 243, which is not a, if I put that into my calculator, I'll get a decimal out. It's not going to be an integer. It's not a perfect square. So depending on the problem, you might do a decimal approximation or you might do simple radical form. So just in the interest of time here, I'm going to do a decimal approximation. So I'll put that in as about 15.59. Okay, so I just found this piece, and that's the missing part in my area formula over here. Okay, so since this is a decimal approximation here, I want to change this sign to say it's about equal to that. Okay, and then 1/2 of 18 is 9. Don't distribute that 1/2. You only do that if you've got multiple terms separated by plus or minus signs. So I'm just multiplying those together. Okay, and then I still have that decimal in my calculator, so I might as well use the whole thing. It's good to wait till the end of the problem to round. So I'm going to multiply that by 9, and then I'm going to get about 140 I'll call that 140.3. So my area is going to be about 140.3, and I know the units, they're centimeters, and since it is area, it's square centimeters. So there we go. Okay. So you cut the triangle in half, use Pythagorean theorem to find the height, and then you can do the area formula, okay? All right, so next up, the main topic in this section is this kind of a situation where we've got a right triangle that's cut into two smaller right triangles, okay? I've got the big right triangle, and then I'm going to color code the other ones. So my medium triangle, I'm going to use my pink highlighter for that. Okay, that's going to correspond to this triangle down here. Okay, so I'm off screen, sorry. It's going to correspond to this medium-sized triangle. That one's embedded right there. What I did is I took the medium and small triangles and drew them separately. Okay, and it's not exactly to scale because I just did it with my computer, but without measuring. But this is also a right triangle right here, right? Has to be. And then so this is supposed to represent the small triangle, okay? So what's going to happen with these triangles is they're all going to be similar triangles, okay? And we could, I could show you that with the right angles, and then also with the shared angles. Some of these triangles have shared angles, okay? And in the interest of time, I'm not going to go through that process, but these are all similar triangles, and that's the key to solving these problems, okay? So what I'm going to try to do is, I've got my big 3, 4, 5 triangle. I'm going to try to put, for this pink triangle, the x, y, and 4 in the right positions here, okay? So the x is going to be the smaller leg, so I'm going to put that right here. And the y is going to be the longer leg in the pink triangle, and the hypotenuse of the pink triangle is 4. Okay, and I'll do the same thing with the green triangle. So the hypotenuse is 3, right? And just by the looks of it, z is the smaller side, the shorter side, and x would be the longer one, okay? And now what I can do, I can set up some proportions. I have all the sides of the big triangle. So let's say I'm trying to find x. Well, these are all situated the same way. So if I look at the big triangle, 3 is going to be to x. And I could say 3 is to x as 4 is to y, but then I'd have 2 variables, right? So I want to find 2 sides that match up where I have both numbers. So I'm going to use the 5 and the 4. Okay, so 3 is going to be to x as 5 is to 4. So I'm going to set up a proportion like that. 3 is to x as 5 is to 4. Okay, and then I'm going to cross multiply. This is more or less what we were doing in the last chapter, in chapter 8, right? So I've got 5x equals 12. And then x would be 12 fifths. Or 12 fifths as a decimal is going to be 2.4, either way. Okay, so there's x. We found x. Let's go ahead and try to find y. We're going to do the same kind of thing. So I definitely want, I've got 2 different y's. I could use either one of these. It doesn't really matter. But I'll use this one here. Okay, so this is the bottom of this triangle. I don't want to compare it to the x because then I got 2 variables, but I can compare it to the 4. Okay, so I have the y and the 4. And let's see, I need to choose 2 other pieces in these 2 triangles where I have both numbers. So I don't want to use the 3 and the x, but I can use the 5 and the 4. So I can say 5 is to 4 as 4 is to y. 5 is to 4 as 4 is to y. Right? Here, so I'll do that up here. 5 is to 4 as 4 is to y. There we go. Cross multiply again. So 5y is going to equal 16. And then that's 16 fifths or 3.2. Okay. Now, another technique you can use, anytime you get 2 sides of a right triangle, you could find the 3rd side. So, you know, down here, I have x now, so I could plug in 2.4 for x and then do Pythagorean theorem here. Okay. I'm just going to continue doing setting up proportions, but once you get enough pieces, you can also use the Pythagorean theorem. Okay. So I still need the z, so I'm going to use this down here. And I want to match that up. I don't want to match it up with the x. I want to match it up with the 3. Okay? So 3 is to z as, and then I need 2 pieces in these same 2 triangles. I'm not going to use anything from the middle-sized triangle. I want to use the big triangle and the small one. I need 2 corresponding pieces. I have both of them. That would be the 5 and the 3, right? So I'm going to say 3 is to z as 5 is to 3. 3 is to z as 5 is to 3. Okay, cross multiply. 5z is going to equal 9. And then divide by 5. So z is going to equal 9 fifths, which is also 1.8. Okay, and now I solve for x, y, and z. There we go. Okay. All right. So there's another problem. Just like this on the next page. Instead of a 3, 4, 5 triangle to begin with, we've got a 5, 12, 13. Okay. All right, so let's try that one out. Okay, so on this next page, the triangles aren't drawn separately like they are here. That's what I would recommend that you do. Okay, and if it's helpful, color code it to make it easier to get the pieces in the right place. So I'm going to take this diagram, I'm going to treat this as my big triangle, and I'm going to sketch out a medium and a small triangle that are also turned in the same direction, because it makes it easier to set up the proportions. Okay, so that's my plan here. All right, so I've got my big 5, 12, 13. So I'm going to take, I'll have this be the medium one. Okay, and I want to draw that so that it's kind of facing the same direction as my big triangle, like that. Okay, and then when I'm looking at the shorter of those two legs, it's the X. When the longer leg I don't actually have. It's part of 13. I don't know how much, so I'm just going to leave that blank for now. But I do have the hypotenuse, which is 12. Okay, so there's my medium triangle. And then I'm going to paint my small one green. Okay, also I'm going to put in that right angle right there, because there would be a right angle right there. All right, and I'm going to kind of turn it around. There's my adorable small triangle. Okay, and then X is the longer of the two legs, and 5 is the hypotenuse. Okay, now we don't really need all three of these triangles for this problem, because we're only finding the X part. Okay, but now we've got some options. So if let's say I'm just using the middle triangle. I don't really need this one. I just need one of these two triangles here, because I can match up either of these X's. So hey, that X matches up with this 5. Okay, so 5 is to X, and then I need two pieces in these same two triangles where I have both parts. So I'm using the 5 and the X, so 5 is going to be to X as 13 is to 12, right? And I can set up a proportion from there. 5 is to X as 13 is to 12. Okay, cross multiply. 13x is going to equal 60. Divide by 13, and I'm going to get 60 over 13, which is already reduced, but you could write it as decimal as well, although it wouldn't be exact. It would be about 4.6. Okay, all right. So moving on, I'm going to go in a different direction for a sec, but this is actually going to tie in. All right, so you've probably seen problems where you're asked to find the mean of two numbers. So the mean is the average. Okay, so if I wanted to average 2 and 18, I would add them together and then divide by how many of them there are. There's 2 of them. So the mean there is going to be 10. Okay, now when you're asked for the mean, that's really actually the arithmetic mean. So if they don't say what kind of mean we're talking about, it's called the arithmetic mean. Okay, that's the kind where you add together the pieces. Okay, but there's something else called a geometric mean. The geometric mean in this sequence, the geometric mean is going to be the number in this sequence that goes in between 2 and 18. It's not going to be 10 though. It's going to be the number where you can multiply by the same thing to get from one number to the other. Okay? So the geometric mean, I'm going to multiply by something to get this blank number, and then multiply by something else. But that I shouldn't say something else, by the same thing. Okay, so I'm calling that R for the ratio. But I'm going to multiply by something, okay? And this one, you might be able to kind of just try some things. If I multiply it by 2, then 2 times 2 is 4, and I multiply by 2 again, I get 8. Okay, that's not going to work. Let's try 3. 2 times 3 is 6. 6 times 3 is 18. So hey, this is going to actually be the number in the middle would be 6 if you're multiplying by 3 to get from term to term. So sometimes you can kind of just think through it, but that's a pain. And imagine I had large numbers or decimals or fractions or something like that. Okay, 6 is going to be the geometric mean of 2 and 18. So I was just showing you that way so you understand what the geometric mean is. Okay, with the arithmetic mean, we had 2, 10, and 18, and we're adding the same thing. We're adding 8 here, right, to get from term to term, and that means 10 is going to be right in the middle. But this is different because with 2, 6, and 18, we're multiplying by the same thing. We're multiplying by 3 here. Okay? All right. So we can also solve this with a proportion. Okay? This is that x is the geometric mean of a and b. So here's what I'm going to do. The two numbers that I'm finding the geometric mean of, which are a and b here, I'm going to set up a proportion. A proportion is two fractions that are equal. Okay? I'm going to put the a in the top left corner. I'm going to put the b in the bottom right corner. So they're in diagonal corners from each other. Okay? And the part that is the geometric mean is going to go in both of the other slots. So in both of these slots, I'm going to put x. That's going to be the geometric mean. Okay? And now what we can do, we can solve for x. Okay? So I'm going to cross multiply. So x times x is x squared. It's not 2x. X plus x is 2x, but x times x is x squared. And then a times b is ab. Okay? Now, if I want to find the geometric mean, I'm going to take the square root of a and of both sides of this equation. So I'm going to get this. Okay? Now, technically, it could be the positive or negative root, but let's just do the positive roots for the time being. Okay? So you can always go through with this process. When I'm finding the geometric mean of 2 and 12, I could set it up like that and put x's in the opposite corners and then cross multiply. Okay? And that's totally fine. So I'm going to have x squared is going to equal 24. Okay? And I'll take the square root. I'm going to go ahead and put this in simple radical form because it's not a perfect square. So I'm breaking up the 24, so I don't know, 4 times 6, right? I'm looking for twins here. I can break up the 4 into 2 times 2. I can break up the 6 into 2 times 3. Okay, and then anytime you have a pair of twins, yeah, there's 3 2's, but the twins are going to make a jailbreak, right? One of them is going to get out, the other one won't. But then those two are going to be stuck in there, so I got 2 times 2 times 3. I multiply it all together, 2 root 6. So 2 root 6 is the same as root 24, okay? You can always go through with setting up this proportion, but you can also just kind of memorize this formula. So if I want the geometric mean of 3 and 12, it's going to be the square root of 3 times 12. 3 and 12 are going to be my a and my b, okay? And that's actually what happened here, right? 2 times 12 is 24. I took the square root of 24, okay? So it's just a nice little shortcut if you memorize this little formula. But if you don't, you can always set up a proportion, okay? And again, I'm going simple radical form here. So rather than multiplying this together, actually, if I do multiply it together, I just noticed it is a perfect square. So this is going to come out to exactly 6. Okay, and it makes sense. 3 times 2 is 6, and if I multiply by 2 again, 6 times 2 is 12. Okay. All right, let's try one more down here. I'm going to find the geometric mean of 5 and 12. I'm going to use this little formula. Okay. Then I'll break apart the 10. I could multiply it to get 50, but it's not a perfect square. Okay, now I found some twins. So these are going to make a break, right? One gets out, one doesn't. So this is going to be 5, and then 2 stuck in there, 5 root 2. Okay. Okay, so now I'm going to apply this back to this situation where we've got a big right triangle cut up into 2 smaller right triangles. Okay. So when this happens, if you've got a triangle cut up like this line in the middle is going to be the geometric mean between A and B. Okay? This is the geometric mean altitude theorem because this is an altitude of the big triangle. It's the height of the big triangle. Okay? So x is the geometric mean of A and B. In other words, x is going to equal the square root of A times B. Okay? So that gives us a nice little shortcut. We could always cut up these, draw these triangles separately instead of proportions, but it's going to make things a lot quicker. I'm just saying, oh, this is an altitude, so x is going to be the geometric mean between this piece and this piece. Okay, so x is the geometric mean between 3 and 6. I can set it up like that. That would be the square root of 18. It's not a perfect square, so I'm going to cut this up or break the 6 up into 3 times 2. Hey, I found a pair of twins. 3 root 2. Some problems might ask you to round to the nearest tenth or something. Then I just put root 18 into a calculator. Okay, and same kind of deal here. X is going to be the geometric mean between these two things. So x is the geometric mean between 10 and 4. I'll set it up like that. Root 40 is not a perfect square, so I'm going to break these up looking for twins. 5 times 2 is 10, and then 2 times 2 is 4. And I can see I got 3 2s, so only one pair of twins though, so one of those will get out. And then I've got a 5 and a 2 still in there. 2 root 10. Okay? All right, next up. So this is a little trickier. On the last two problems, the x was the altitude, but here the 4 is the altitude. So that means this is going to be the geometric mean between these two pieces. So be careful when you set that up, right? When x was the geometric mean between these two, x equaled the square root of the product of those two things, okay? So here 4 is going to equal, I'm putting the 4 on the left because that's the part that's the geometric mean. And then underneath the radical, I'm going to put the product of those two. You could say x times 3, but I'm just going to say 3x like that, okay? 3 times x is 3x, okay? Now I still have to solve this, okay? This is something that you did in algebra, but we haven't really done in geometry. So I want to get rid of that square root, and the opposite of a square root is squaring something. That's going to get me just 3x on the right side of the equation. I can do that as long as I square the whole equation, so I've got to square the other side too. Okay, so 4 squared is 16, and then I've got just 3x over there, and I've almost got x now. Just multiply by, or divide by 3. So x is going to equal 16 over 3. Okay. All right. We can also set up a little shortcut when we're dealing with a leg. Okay, this time I don't have this piece marked like I did on the last couple of problems. So it's not the geometric mean altitude theorem. It's the geometric mean leg theorem because x is a leg, so we're looking for x. Okay, so here's how it's going to work. X is going to be the geometric mean. So this part will be the geometric mean. Not between A and B though, because this part I highlighted would be the geometric mean between A and this piece. This is going to be different, okay? So, sorry, it is between A and B, but it's not between this piece and this piece. See the difference here? So this is how I remember. A is the part of the hypotenuse that's close to the x, and then B is the whole thing. So I think of it as the leg is the geometric mean between the close piece and the whole thing. So I'm going to say between the close segment and the whole hypotenuse. Okay, so algebraically, here x is going to be the geometric mean between A and B. It's going to look like that, okay? So let's try it out here. So here's the mistake. People are going to say, oh, x is the geometric mean between 3 and 8. It's not. Y is the geometric mean between 3 and 8, okay? So actually, let's do that part first. So y is the geometric mean between 3 and 8. Okay, that would be root 24. Hey, we just did that somewhere earlier, root 24. But it's not a perfect square, so let's break up the 8. 4 times 2, or 2 times 2 times 2. Okay, and I got a 3 and a 2 left in there. So 2 root 6 is y, okay? When I'm looking for x, though, x is the geometric mean between the close piece and the whole thing. The whole thing is not 8. The whole thing is going to be 11, right? So x is going to be the geometric mean between 3 and 11. Okay? And I can't break either of those up any further. So there's no twins in here, so I'm just going to call that root 33. Okay? Now, z is going to be the geometric mean between the close piece to it. So the 8 is closer than the 3, right? So between the close piece and the whole thing, so z is going to be the geometric mean between 8 and 11. So I'm going to set it up like that, okay? Can't break up the 11, but I can break up the 8, and I think I'll find some twins in there. Hey, there's some twins. So this is going to be 2, and then 2 times 11 left in there, so 2 root 22. Okay, and that's it. See you next time.